Multi-head attention is the engine behind almost every major breakthrough in AI over the last few years. From the LLMs we use daily to the diffusion models generating hyperrealistic images and video. But attention has a fundamental flaw: quadratic complexity. As your input sequence grows, the computational cost doesn't just increase, it explodes. This bottleneck has forced researchers to make trade-offs. We have linear time approximations like linformer, but those often require fixed sequence lengths. We have state space models, or SSMs, which are incredibly efficient but impose a causal ordering that doesn't always make sense for non-text data, like images or 3D point clouds. The question is quadratic complexity actually necessary to match the performance of attention? A new paper introduces the Polynomial Mixer, or PoM. PoM is designed as a linear time, drop-in replacement for self-attention that maintains the expressivity of a transformer without the quadratic overhead. To understand how PoM works, we first have to look at what it's trying to replace. In standard multi-head attention, every token interacts with every other token. This is why it's so powerful, but also why it's so slow. PoM takes a different approach. Instead of pairwise interactions, it uses a shared state representation. Think of this as a common memory that every token in the sequence can access. PoM aggregates the entire input sequence into a compact representation using a learned polynomial function. Mathematically, if we have an input sequence x of n tokens, PoM summarizes this into a single representation, h, x. This is done by mapping the tokens into a higher dimensional space and applying a polynomial of degree, k. The system uses learnable coefficients and an activation function to create a summary of the global context. Once this global state is computed, each token queries that shared representation using a gating mechanism, essentially a sigmoid-activated wait, to retrieve the specific contextual information it needs. This result is then projected back into the original dimension. Because these operations are linear relative to the sequence length, the computational cost is drastically reduced. Now, for the technical crowd, the most important part of this research isn't just the speed, it's the contextual mapping property. This is a theoretical requirement for a model to be a universal sequence-to-sequence approximator. Most linear alternatives like MLPs, CNNs, or even SSMs don't satisfy this property. However, the authors prove that PoM does. This means that a polymorpher, a transformer where attention blocks are replaced by PoM blocks, is theoretically as potent as a standard transformer. But does it actually work in practice? The researchers tested PoM across 5 completely different domains to see if it could truly act as a general-purpose replacement. First, in natural language processing, they trained a 125 million parameter GPT-2 style model. They found that while a pure PoM model performed slightly below full attention, a hybrid version, which alternates between PoM and local attention, actually matched or even surpassed the performance of the original GPT-2 while being significantly more efficient. In terms of throughput, PoM-based models were substantially faster than transformers and even outperformed Mamba at various sequence lengths. They then moved to optical character recognition. By replacing attention with PoM in a vision transformer, they saw that for short sequences, attention is still competitive due to GPU optimization. But as they scaled up to processing entire pages of text, increasing the token count to around 2,000, PoM provided a significant speed-up over flash attention while maintaining the same character and word error rates. In Earth observation, they used PoM for crop type mapping from satellite time series. Here, the results were even more dramatic. The PoM variant was over 300% faster than the baseline, which is critical for geospatial data where you're dealing with high-dimensional spectral bands and long temporal sequences. They also tackled 3D point cloud segmentation. Using a hybrid PoM v3 architecture, they matched the state-of-the-art point transformer v3 while reducing computation time. A major practical win here is that PoM's linear complexity allows the model to process entire point clouds in memory without the need for chunking. Finally, they tested class-conditional image generation using the CT architecture. They created CPoM, and the results showed that the visual fidelity measured by FID was identical to the attention-based models. The real difference appeared at high resolutions. Once they hit 1024 pixels per side, the quadratic cost of attention becomes a wall. CPoM, however, scaled linearly, making high-resolution generation significantly faster. So what's the takeaway? The Polynomial Mixer proves that we can achieve the performance of multi-head attention without the quadratic tax. By using a learned polynomial function to create a global context, PoM provides a path toward models that can handle massive context windows, like high-definition video or massive multimodal datasets, without crashing our hardware. While the current implementation is in high-level PyTorch, the authors expect that once dedicated CUDA kernels are written for PoM, the speed gap between this and traditional attention will only widen. We are looking at a potential shift toward a new generation of efficient, attention-free sequence models.